Hello and welcome to another video for our differential equations class. We're going to give an overview of Module 6, where we start looking at second order differential equations. And so we want to get used to some of the changes going from first order to second order. The differential equation itself, remember in first order only had a first derivative. We will now see the second derivative. We won't always see the first derivative, but it could be there. The initial conditions for first order was just the value of the solution at a point. We now need two initial conditions to make it an initial value problem with a specific solution. And in general, the number of initial conditions will match the degree of the differential equation. Now we'll often have both the initial conditions be the solution and its derivative evaluated at the same point. That's the idea with the initial value problem. If those are the solution evaluated at two different points, or even the solution and its derivative at two different points, that's more of a boundary value problem, which would be covered in another class. Now, the general solution for first order, right, we've seen that had the single constant c, and we would determine the value of that constant using the initial condition to get the specific solution. Well, since we have two initial conditions for second order, we will have two unknown constants, C1 and C2, and they'll be next to the two linearly independent solutions. So at the end of the day, there will just be kind of one big general solution or one specific solution, but we can think of it as having parts, and that's helpful at times. So we will have to refer to those as y1 and y2, or the fundamental set of solutions. And then, of course, C1 and C2 would be determined from the initial conditions. So our general solution will have two C's. For restricting to linear second order ordinary differential equations, we have a general formula in the book where we identify the coefficient functions with a capital P and subscripts. So P0 of x is the coefficient function in front of y double prime, P1 in front of y prime, and P2 in front of y. And then still using f for our right-hand side forcing function. Now, you might also see other forms of this, and I think the author does this as well, dividing everything by that leading coefficient function, P0, and then just having y double prime by itself as a term. And then P of x for the function in front of y prime and Q of x in front of y, and then still using f. And then, of course, that's the non-homogeneous form of the linear second order ordinary differential equation. Going to homogeneous form is the same idea as first order, where the forcing function is 0. All of this is going to be more complicated, and so one of the cases we spend a lot of time on is a simplified version of this where those coefficient functions are just constants. So then you'll see a general form for the second order linear homogeneous constant coefficient ODE. And we use A, B, and C for those constants when they are not known. So before we learn how to find the solution to that type of differential equation, it's nice to connect it to what we already learned about first order. Remember the first order linear homogeneous ordinary differential equation, which was our second methodology in the course. And we learned how to solve that, and then saw there was like a shortcut formula where we'd have the solution y is equal to base e exponential e to the negative integral of p of x dx, where p of x is that coefficient function in front of y. Again, you can just subtract the p of x y to the other side, and then sort of do a separation of variables, integrate both sides, and then raise both sides to base e exponential. So what if p of x was just the constant function 5? What would our solution be? Pause the recording if you need some more time to think about it. But subtracting over there and then dividing by y and then integrating The integral of -5 is -5x. And of course, we would have a plus c. But if we let c be equal to 0 for now, and then just make both sides the exponent for a base e exponential, we see it is just e to the -5x. So we didn't look at that as kind of a special case of that function p of x being a constant. But if it is, then you can actually jump right to the solution because it just makes the opposite of that constant be in the exponent. So the correct answer is C. All right, so going back to this second order constant coefficient homogeneous linear ordinary differential equation. Let's now put in some values for constants. A is 1, B is 5, C is 6. And let's say we're trying to solve that. Again, thinking about a function and its derivatives being adding up and going to 0, you would expect that they would be like terms, right? And so what kind of function has derivatives that are like terms with it? Of course, our friend base e exponential. So let's just take a stab at the solution being e to the -5x. And then, of course, with the derivatives, we do get that chain rule effect of -5 and then +25 coming out in front of its coefficients. All right, substituting those in, we see that these are all like terms because they all have e to the -5x. In fact, the first two terms are opposites, right? 25 e to the -5x and -25 e to the -5x. So those would add to 0. Of course, the whole thing isn't equal to 0 because of the 6 e to the -5x. But it makes you think that if we just chose the right number instead of -5, maybe we could get it so that all of these added up to 0, and then we would have a solution. So what is that number that goes in front of x in the exponent? So we want to figure out what that number is, and we'll use the variable r for that. You may see other symbols being used. And then if we take derivatives of e to the rx, we know that the chain rule will give us r and r squared in the first and second derivatives as a coefficient. And then we can substitute that in. And no matter what we choose for r, these will all have e to the rx. E to the rx is non-zero, so we can divide everything by that. And this will always result in a quadratic equation for r. In this case, r squared plus 5r plus 6. This is referred to as the characteristic equation for the ODE. You'll notice that the coefficients in this quadratic match the coefficients a, b, c in the original ODE. And so once you've done this a few times, you could jump right from the differential equation to the characteristic equation. Now, of course, we know how to solve a quadratic equation from pre-calculus, and we can try techniques such as factoring and the quadratic formula to find the values of r. And we know that there could be two real solutions, one repeated root, or complex solutions in the form of a complex conjugate pair. And depending on the nature of those solutions, we'll have to look at the nature of the fundamental set of solutions, y1 and y2. Of course, that'll all be covered in the methodology. So finding the solutions of this kind of pre-calculus problem ends up becoming the basis for solving an important set of real basic second-order linear differential equations. All right, that's all it for now, but as always, we're going to attribute William Trench with the wonderful textbook Elementary Differential Equations with Boundary Value Problems, which is CC by NCSA. Thank you very much. I'll see you in the methodology video or the next overview video.